reevaluate crop rotations. Golong is going to start us off. He is an outreach specialist covering the central part of the state. And I'll pass it off to you, Golong.
Thank you, Laura. Can you hear me all right? Just double checking.
Sounds great.
Okay, let me share my screen. Okay, does that look all
Looks
right?
perfect. Yep, looks great.
Thank
Thanks,
you.
Golong.
Oh, thank you, Laura. And for the next 20 minutes, we will talk about what a nitrogen balance is, why can all farms benefit from understanding nitrogen balance, and what could be changed for cleaner water. Like Laura said, I'm Guolong Liang. I'm an outreach specialist joining you today from Central Wisconsin, Stevens Point. And in my presentation today, I will use Wisconsin Central Sands as an example to frame our conversation. This time, I'll just give you all the takeaways right away. So what are we going to learn today? We'll start with why should we reduce nitrogen loss in the first place? What is the first step towards reducing nitrogen losses? And what are some approaches to reduce loss over crop rotations in the example of Wisconsin Central Sands? We'll take time to break these approaches down one by one through our time today. To start, why should we reduce nitrogen loss in the first place, right? Because it benefits us all. Reduction of nitrogen loss for farmers means increased profitability and better stewardship of our water and fertilizer inputs. For our communities, the reduction means cleaner drinking water and less risks of cancer, thyroid diseases, and adverse birth outcomes from elevated nitrate levels within our drinking water. For our ecosystem, reducing nitrogen loss means fewer algal blooms in Wisconsin lakes and streams, the Great Lakes, as well as the Mississippi River watershed. Today, we'll focus on the Central Sands area of Wisconsin as an example to investigate potential agricultural solutions in the area. For those who are not familiar with Wisconsin Central Sands, it is a geographic region that is characterized by a sandy aquifer with a shallow water table below the surface located in the central part of the state. It has provided ample water and resources for agriculture and our communities. Several crops within the region play important economic roles for the nation. One of the examples is potatoes. Wisconsin produced the third most potatoes in the nation, according to U.S. Department of Agriculture's report in 2023. Potato industry alone generates more than $400 million in economic activity for the state. However, the prominent landscape of high-value vegetable crops also come with consequences, one of which being water quality. Potato, field corn, and sweet corn all require high nitrogen input to reach desirable yield on sandy soils with low organic matter. Presence of unused N in highly permeable soils, flushed with heavy precipitation, leads to increased leaching risks under the cropping systems around here. On the left, we're looking at a map of Wisconsin showing the percentage of groundwater samples in each township above the 10 milligrams per liter nitrate nitrogen drinking water standard. From the map, we can clearly see that Wisconsin Central Sands being one of the hotspots for nitrate contamination. At the same time, a lot of where we saw elevated nitrate levels in the Central Sands also appear to be where our agricultural production is focused on. So what are some incremental steps a farmer can take to protect water while staying profitable? Today, I'm going to propose that the first step can be to build a field-based nitrogen balance. But what do I mean by that, right? Nitrogen in nature already cycles from our atmosphere to our soil and to our water. With agriculture, we introduce extra nitrogen to the system as inputs, and some of the inputs highlighted here are crop residue, manure, compost, those that are fixed by legumes, synthetic fertilizer N, as well as nitrogen within the irrigation. However, with agriculture, nitrogen is also removed from multiple sources, such as crop harvest, volatilization into the air, denitrification, and of course, leaching, which one output that we're gonna focus on today. When we put leaching, inputs, outputs, and changes in soil and into an equation, we can then estimate the leachable nitrogen on a year-to-year basis. If you would like to learn more about this approach, feel free to check out my colleagues Kelsey and Lindsay's webinar linked in our chat and in our website, where they took a deeper dive into this approach and presented on some of the Discovery Farms leaching data from the past years. While single-year nitrogen balance serves as an annual recap, right, as how we did in terms of nitrogen leaching, multiple-year nitrogen balance can guide our management strategies, including crop rotation. In this example of us managing 4 fields, we can track how we manage them and be aware of leaching risks each year and each crop with specific inputs and yield data that we have at our hands. Over time, we can then to think about the ways to decrease such risks from rotation to rotation with clear note-taking and record tracking. Now we're going to take a closer look at how Wisconsin Central Sands does in terms of its nitrogen balance over crop rotations. What crops and rotations are potato growers in the Central Sands growing and using, as you may ask? From the movie on the left, yes, it's playing. We can see that the pixels changing colors representing the changes in crop type for each year. According to Heinemann and Kucharek in 2019, the majority of potato growers use a 3-year crop rotation, meaning that they come back to the same field to grow potatoes after around 2 years. Some of the typical crops that they rotate potatoes with are sweet corn, field corn, snap beans, peas, and soybeans. So in a nitrate study where we conducted in a nitrate study that we conducted on sandy soils within the 4-year potato rotation, we observed high leaching under multiple cropping systems within this rotation. The most leaching that was observed are under potatoes and sweet corn, with field corn and peas and millet double cropping totaling around 359 pounds of nitrogen per acre for total leaching. So what are some approaches for us to reduce this number, to reduce the overall leaching loads within the system? Here we go into the approaches to reduce leaching losses, right? And the first one is extend the crop rotation. In the Central Sands, this is not a new concept at all. This is a cover we got from an extension bulletin in 1952 discussing the benefits of longer rotation and better use of lime and fertilizer to manage crops in Wisconsin Central Sands. And here we are 70 years later, wrangling with the same problem, just from a different perspective, this time on water quality and environmental stewardship. From the satellite, we saw that over 20% of the acres are grown with continuous potatoes or rotated with only 1 year off of potatoes. Here we're looking at the comparison of leaching potentials using a 4-year crop rotation and a 2-year potato sweet corn rotation. I'm going to drive your attention to the bottom row here where we talked about the total projected leaching losses. In the 4-year crop rotation, we have close to 360 pounds of nitrogen per acre loss. While if we only use a 2-year rotation, that number becomes 502. We can also calculate the annual average leaching by dividing the total leaching over 4 years. So how do these two different crop rotations affect water quality differently? In an average year of 13 inches of drainage within the 4-year rotation, the annual nitrogen concentration coming out of that drainage water is 30 parts per million on average, while that number in a 2-year crop rotation is 42 parts per million. In a wet year, though, with 20 inches of drainage, the concentration for nitrate nitrogen for each rotation decreases to 20 and 27 parts per million. Of course, this is using the budget approach to assume that the leaching dynamics within the 2-year crop rotation to be identical in both times, which is not realistic in real life. Because concentrations can be affected by the amount of rainfall and snow melt, as well as unused nitrogen within our soil by the end of the growing seasons. The second approach to reduce nitrogen loss across rotations is to zone in into individual crops and become more efficient in using nitrogen in those years. We'll start with an example of sweet corn. From the leaching study, we saw that more than 100 pounds of nitrogen per acre were lost during the sweet corn year. Are there any ways where we can do better in the sweet corn to reduce such loss? The answer is yes, and the key is the word efficiency. Right here, we're seeing a balance. The nitrogen from the fertilizer on the left overweighs the amount of sweet corn that can the amount of nitrogen that the sweet corn can remove from the soil on the right. We are seeing an imbalance, which is caused by such a difference within the amount of nitrogen that between the input and the output. And this causes higher risks for leaching. However, efficiency can mean a lot of different things depending on the context. So what do I mean by efficiency here? Well, two very simple concepts, right? In order to get higher efficiency, we can either reach for higher yields with the same amount of input that we have. Here, doubling the sweet corn yield might be unrealistic, but any incremental increase in yield without applying more has a water quality benefit. Or we can try to reach and sustain our target yield with less input. Can we decrease the amount of fertilizer we use while still maintaining acceptable yields? Researchers at UW have conducted nitrogen response trials on both sweet corn and snap beans over the years to answer this question. Today, I'm presenting our research conducted by the Roark Lab from UW-Madison to demonstrate these two strategies with data. Because let's take a closer look at sweet corn first. In this trial, they applied different nitrogen rates on sweet corn and tested how much nitrogen did each strip remove. On the x-axis, we can see nitrogen from fertilizer, and on the y-axis, we're going to talk about the distribution of nitrogen uptaken by the sweet corn and some unused nitrogen from the budget approach. In this graph, we can see that as we applied 140 units of N in the form of fertilizer, sweet corn took up 76% of that, as 34 units of nitrogen was left unused after plant harvest. As more nitrogen was applied, we can see that the plant becomes less efficient in uptaking applied nitrogen, and we reach 200 units of and when we reach 200 units of fertilizer applied nitrogen, and when we can see that only 60% of that ended up in plant tissues, while 80 pounds of nitrogen per acre was not used. These unused nitrogen poses significant risks for leaching, especially for crops that are harvested grain with heavy residue left on the field after, such as sweet corn. Now switching gears to snap beans. Here we're looking at the relationship between yield and uptake efficiencies for snap beans. In this line, at the nitrogen uptake efficiency over yield when we apply 125 units of N. We can increase uptake efficiency and protect water better if we increase yield without applying more, right? Note that all the data points on this line was applied with the same amount of nitrogen. And if we take a closer look at the lower end of this line, if we apply 125 units of N in this line and only got 6 to 7 tons of beans, then the leaching risks will be high because of the unused nitrogen. Or if we're reaching for our yield goal, say at 7 tons per acre, the less nitrogen we use, right? The yellow and the blue curve representing the relationships under a lower nitrogen use scenario. The less nitrogen we use, the higher uptake efficiency we'll essentially get. Again, if we can become more efficient in growing our rotational crops through whichever approach here, we can reduce the overall leaching risks through our crop rotation. Now, the third point I'm looking to make today is to see if we can incorporate some crops that do not demand extra synthetic fertilizers or even can potentially provide a nitrogen credit into the central sands rotation. In order to answer this question, a group of UW researchers tried to understand if the legumes such as alfalfa and red clover can provide a nitrogen credit to the potato crop. Their data included 28 sites all over Wisconsin from Green Lake to Spooner, with soil types varying from loam to loamy sand. Within the context of today's conversation, I was particularly interested and curious to see if such nitrogen credit can be given on the sandy soil. Well, from this paper, the answer is maybe. After alfalfa, potato in 10 out of 12 sites did not respond to applied N. The two that did respond to fertilizer N were at Hancock with loamy sand. As a result, it appeared that alfalfa is providing 0 to 200 pounds of N and an average of 115 units to potatoes. That credit is likely to be taken more in the medium texture soils than on the sandy soils, as we did observe a nitrogen response. Similar findings was observed in potatoes following red clover as well. But now if we take a step back, right, one of the benefits of including a legume in the potato rotation is that it does not require extra nitrogen in order for the crop to grow. This by itself provides water quality benefits. And another example within this group is soybeans. However, we do need to recognize that more leaching monitoring under legumes on sandy soils is needed for us to better understand the nitrogen balance dynamics for that specific combination. When there's a demand and the room for a resting year or two, we can also consider other crops like the ones presented here. Some small grain examples include oats, barley, and wheat. These grains can be used for forage as well. Our colleagues at the Clubean team, led by Dr. Sean Conley, have done a lot of work on the agronomics on small grains, so feel free to go to their website for more information. One other alternative crop that has been brought up in the water quality conversation a lot these days is intermediate wheatgrass, also known as kernza. Its long roots and its perennial habit allowed for promising water quality benefits, as it can also serve as a forage as well as a grain. However, both small grains and kernza seem to face similar challenges in Wisconsin and even nationwide, and that is where the demand is, right? The demand for kernza, for example, is still very variable depending on the use as well as the region. Currently, more work is being done to build more awareness as well as the supply chain for an alternative grain crop market, especially for the local food economic scene. Last but not least, let's go back to the fundamentals, right? With our crop rotations, let's make sure that we're covering our shoulder seasons to minimize our leaching losses during the off season. Cover crops are necessary in the central sands, and most of our growers use cover crops because of wind erosion. But its nutrient retention benefits should not be overlooked, and we should think deeper into how we can use cover crops for the sake of nitrogen balance. In the same nitrate leaching study mentioned before, we found that 60% of the nitrogen loss that happened during the 4-year monitoring period occurred during the off season from harvest to planting versus growing season. So what can we do to better cover our grounds all year round? What's important here is focusing on the shorter season crops within our crop rotation. We're talking peas, snap beans, and sweet corn specifically. Because of a shorter growing season for our cash crop, we can give our cover crops a better chance of developing that biomass for water quality benefits. But it's also a fine balance, right, between having too much biomass so that it makes farm logistics more challenging, but still maintaining that water quality benefits that we are striving for. Some of the other common options for cover crops recommended in the state are winter rye, barley, clover, as well as brassicas. There have been more research from Minnesota as well as locally here done on winter camelina, which can generate economic return potentially from its use as a sustainable jet fuel. And that brings us to an exciting transdisciplinary project that has been happening with a group of researchers at UW who are also working on a variety of different management practices in agriculture to improve our groundwater quality. Feel free to check out the link in the chat to learn more about this project and our events in the future. Hey, 20 minutes just flew by. So what did we learn today? We talked about the why and the how to build your first field-based nitrogen balance and multiple approaches like extending rotation length, increase nitrogen use efficiency, incorporating low nitrogen demanding crops when we can, and cover the basics, right? Make sure the shoulder seasons are covered with cover crops for water quality benefits. Although we've been focusing on sandy soils and vegetable production today, these principles, the principles behind these recommendations, like balance, uptake efficiency, and using alternative cropping system should apply to other regions as well. Thank you for your attention, and feel free to reach out to me via email or our team from contacts in this snapshot or from our website. I'll pass it back to Laura.
Thank you so much, Go Long. What a great presentation. As we transition here into Stevens, we're going to launch a quick demographic poll. This anonymous information helps us evaluate the audience we're reaching. We appreciate you for filling this out as always. And just a heads up, at the end of the webinar, we're going to launch a second poll that will be more specific to this webinar. And again, any evaluation data helps us improve future programming. So I'll keep this up for another little bit. Okay. And it looks like Stephen has his presentation up, so I'll introduce him quick while we finish answering this poll. Our next speaker is Dr. Stephen Hall. Stephen is an assistant professor and extension specialist in the Department of Plant and Agroecosystem Sciences at UW-Madison. He focuses on agriculture and water quality. Take it away, Stephen. Your presentation looks great. Yep.
Thanks, Laura. That's great. So thanks to all of you for joining us this afternoon. I'm going to pick up sort of where Go Long left off and share some more specific examples of this nitrogen balance approach. Really bringing some long-term data to bear on this question of nitrogen sustainability. So we're going to move from the Central Sands region down into South Central Wisconsin to an experiment on the Arlington Ag Research Station. But before I go any further, I'd really like to acknowledge my co-authors. So Hariom Yadav is a PhD student in my lab. He's done most of the work that I'll share today. And then Greg Sanford is an assistant professor over in the Soil and Environmental Science Department and a really key collaborator on this work. So as Go Long highlighted, these relatively simple back of the envelope calculations I think are really powerful for evaluating nitrogen sustainability. And so what I'm going to discuss today is what we call a partial nitrogen balance approach, where we are thinking about our agronomic nitrogen inputs to our cropping system, as well as our harvested outputs. And so in terms of our inputs, we're thinking about sources of nitrogen like biological fixation, shown here by this root nodule, manure, and synthetic fertilizer. And in terms of our outputs, right, these are different across our systems, but often include grain, as well as the vegetables that we saw in Go Long's presentation, silage and hay, as well as the gain of any the biomass gain of any animals that might be grazing in our cropping systems. And you might ask, well, this is incomplete, right? Why is this partial nitrogen balance useful? And it's useful because these red arrows are relatively straightforward things that we can measure. Whereas, as Golong highlighted, right, these blue arrows, things like nitrate leaching and gas emissions of nitrogen, can be really hard to measure. And so we can actually use these simple to measure quantities to let us at least constrain how large nitrate leaching might be in some of our systems. And so I'll walk you through one of those calculations. So say you're growing corn and you apply 150 pounds of synthetic nitrogen fertilizer. Hopefully you get a good yield, maybe 200 bushels or so. If that grain has about 1% nitrogen, this means that we're hauling off about 120 pounds of nitrogen in that grain. And so this would leave you about 30 pounds of nitrogen that's left over. Well, what happens to that, right, is unclear in any given year, but it's likely over the long term that most of that is either going to be lost as leached nitrate or in some combination with emissions of various nitrogen gases. So this 30 pounds is sort of this extra nitrogen that we have to contend with as a society. And really just to emphasize, in this sort of nitrogen balance approach, we really don't care about the forms of nitrogen that are entering or leaving. This is really just a bookkeeping approach. We also don't care about the internal cycling of nitrogen. We're really treating these systems like a black box, right? We don't have to pay attention to where that nitrogen is, if it's in plant tissue, if it's in soil organic matter, et cetera, et cetera. It's just what's coming in and what's coming out. And so, over long time scales, if we have enough information, this can become a really, really powerful way to evaluate our systems. But as Golong mentioned, right, there's some other factors that we have to consider. And I think the most important of these is really potential long-term changes of nitrogen storage. So from year to year, we can have a little bit of nitrate left over in the soil profile. Typically, that doesn't last for very long. But what turns out to be really important is what's happening with our soil organic matter, whether we're building soil organic matter over years to decades or whether we're losing it. And that's because this is a tremendous reservoir of nitrogen in our cropping systems. If we have, relatively fine textured fertile soils like we do in many parts of the state, there can be many thousands of pounds of nitrogen bound up in this organic matter. So I'll bring you to what I'll talk about today is some results from a long-term trial here in Arlington, the Wisconsin Integrated Cropping Systems Trial, or WIXT. And so this was started several decades ago by colleagues here at UW and has been maintained over time. And it's really a tremendously valuable resource because of the long-term data that's available, and also because of the wide range of cropping systems that are included in this experiment, which I'll detail in just a second. And again, just want to emphasize that this is a really collaborative effort. We've been able to come in and leverage some of the data that's been collected by numerous other people over the last few decades. And so our specific questions here are, how does this long-term nitrogen balance vary among different cropping systems? And then what are the implications for nitrate leaching potential when we evaluate these different kinds of systems? Okay, so what kinds of crops are included in WIXT? There are 3 different cash grain cropping systems, ranging from a continuous corn system that's managed with tillage, corn soybean that's managed with a little bit less aggressive tillage, and then an organic corn, soybean, wheat, red clover system. As you might imagine, the fertility programs differ quite substantially among these different systems. The continuous corn is relying entirely on synthetic nitrogen. The corn bean system, of course, is relying on synthetic nitrogen and biological fixation during the soybean phase. And then the organic system is relying on composted poultry manure prior to corn, and then biological nitrogen fixation from the soybean and the red clover. And if you're, an agronomist or a CCA and you're looking at these nitrogen rates, you might say these are pretty low, and that's true. These are the long-term averages over the duration of the experiment. These have crept up over recent years, but nonetheless, these are the long-term values that have been applied over the course of this experiment. I'll note that these are sort of chosen to represent overall guidelines consistent with extension recommendations and input from producers. Okay, so 3 other rotations in WIXT. There are 3 dairy forage cropping systems. There is more of a conventional dairy rotation where corn is followed by 3 years of alfalfa. There's an organic dairy rotation with 2 years of alfalfa. The first year oat is interseeded with the alfalfa. And then the last cropping system is managed grazing on perennial cool season pastures that are seeded with clover to provide the nitrogen source. And so in our conventional dairy and our organic dairy rotations, the major nitrogen source for corn production is liquid dairy manure that's applied from a dairy that's right across the street from the experiment. And then during the alfalfa phase, of course, we're relying on biological nitrogen fixation from that crop. And then again, in these grazed pastures, are relying primarily on biological nitrogen fixation by legumes that are seeded in with occasional application of synthetic nitrogen. Okay, so that's the background on the systems. One of the challenges that we have in constructing these partial nitrogen balances is actually getting a handle on how much nitrogen our legumes are contributing. And so if you're familiar with Sean Conley's program, right, Cool Bean, soybeans are a really cool plant in part because they are supplying a good portion of the nitrogen that is used for plant growth. I'll walk you through this figure here. This is a synthesis of global data on nitrogen fixation by soybean for all the studies that these authors could find. And what you have on this x-axis is the nitrogen content of the soybean plant. The y-axis is the nitrogen fixation in that soybean plant. So ideally, if soybeans were, really, super plants, we'd be on this one-to-one line pretty consistently. Unfortunately, beans are cool, but maybe not that cool, right? It turns out, on average, that they supply a little more than 50% of their nitrogen through fixation. And so what this means is, I'll get into in just a second, that these are approximately neutral from a nitrogen balance perspective. We remove about as much nitrogen in the soybean grain as is actually supplied through fixation. And so for these long-term nitrogen balance calculations, what we can do is use different scenarios of fixation in conjunction with our measured yield data to try to guesstimate how much of the soybean nitrogen was provided through fixation. So happy to get into the details if folks are interested. And we're using this similar sort of approach to estimate the nitrogen fixation from the other legume species that are present at Wixt. Okay, so I've talked a bit about the nitrogen inputs to the system, so biological fixation. One of the key advantages of using a long-term experiment like Wixt is that we actually have detailed records of nitrogen as applied to all of these plots, including the manure, which is really a fantastic resource given how variable manure nitrogen can be. In terms of the outputs, we also have really nice data on the nitrogen that's removed in the grain, in the silage and hay, and even in the animals that are grazing on these pastures. And so we can use these measurements to fairly rigorously constrain the nitrogen removal from these cropping systems over time. Okay, so now I'll jump into the data here. And so I'll walk you through this figure. What this is showing is this partial nitrogen balance for all of these cropping systems at Wixt over the 34 years. And so this x-axis is showing you the partial nitrogen balance. Again, a positive number means that there's more agronomic N coming into the system than is leaving in the harvested crops. A negative value means that we're actually removing more N in agronomic products than we're applying. So here at the bottom, we're starting off with continuous corn. So these rectangles here, these are box plots. Essentially, the width of this box is showing you the middle 50% of the data. So it's showing you the variability in this number. And the diamond here is the average. So overall, year over year, on average, there's an excess of about 17 pounds per acre in this continuous corn system. And so we were actually surprised. This was a little bit lower than we might have been expecting, given other results from the region. The corn-soybean system was actually slightly negative here. There's a caveat that this really depends on the scenario that we assume for nitrogen fixation. If we assume that the soybeans are a little bit cooler, a little bit better at fixing nitrogen, this moves us right up to neutral, but essentially not distinguishable from zero. So this is suggesting year over year we're taking out about as much nitrogen in our corn and soybean grain as we're supplying through synthetic fertilizer and nitrogen fixation. Similar kind of story from this corn, soybean, wheat system, although the variability is a little bit wider. The fertility management for this system has changed over the years. It tended to be a little bit more negative in the beginning, tends to be just slightly positive now with the addition of composted poultry manure into this system. So switching gears to these dairy forage rotations, one thing that you'll notice is that these boxes get much wider. And this is really showing the variation among the different phases of this crop rotation, right? We're growing corn and then 3 years of alfalfa, and this nitrogen balance swings from positive to negative, depending where we are in the rotation. Early on in alfalfa establishment, we're adding some more liquid dairy manure, and so we're actually adding more nitrogen than we're taking off. Conversely, by the time we get to the end of the alfalfa rotation with 4 cuts, we're taking a lot of nitrogen off. So even though that alfalfa is fixing a tremendous amount, even if we're taking off a small amount of nitrogen that was derived from the soil, this starts to add up. So similar results overall for these 2 alfalfa rotations at Wixt, but the overall take home is that these are pretty close to neutral from a nitrogen balance perspective. And then finally, the grazed pasture. So we were sort of scratching our heads when we first saw this, right? This is, a relatively small positive number. And, the take home is that there can be substantial nitrogen fixation by legumes in this system, but relatively small offtakes of nitrogen in the form of heifers that are grazing on this system, right? Those heifers are growing, they're accumulating nitrogen in their bodies, right? That nitrogen is walking off the field at the end of the season. But overall, we might have a small nitrogen accumulation. We'll come back to that in just a bit. So I would say overall, for me, the take-home message is pretty good news, right? If we're managing these systems according to extension recommendations, we can have nitrogen balances that are fairly close to neutral, even over the long term. But this brings me sort of to the, the hidden message of this talk, that we also have to consider possible changes in nitrogen storage. So why is this, right? Just to back up, just to reiterate, the dominant form of nitrogen in our cropping systems is typically this organic nitrogen that's stored in soil organic matter. So what is this stuff? This is the products of decomposing plant residues, and even more important, this is really the dead bodies of the bacteria and the fungi that have actually decomposed those plants. So why does this matter? Well, those microbes tend to have a relatively low C to N ratio of about 10. And so this means, right, that our organic matter is really chock full of nitrogen. So why does this matter, right? Well, it turns out that relatively small gains or losses of organic matter can have tremendous leverage over these partial nitrogen balances. So year over year, right, we're really concerned about these red arrows, right, are our inputs approximately balancing our outputs. But if we move to longer time scales, maybe years to decades, these organic matter changes can be really critical. So just to convince you of this, I'll walk you through 2 more simple examples, building on what we talked about at the beginning of the talk. So we're growing some corn, going to apply 150 pounds of nitrogen fertilizer, haul off 120 pounds of nitrogen in the grain, but this time we're going to combine that with an increase of soil organic matter. Say that we adopted reduced tillage, maybe we're growing some cover crops during our shoulder seasons, and we're actually able to increase our soil organic matter by 0.01% per year. This turns out to be equivalent to about 30 pounds of nitrogen that would be stored in the soil organic matter. So under this scenario, we would actually have 0 pounds available for leaching, despite the fact that our red arrows here are slightly imbalanced. Okay, but on the flip side of that, right, what if we have systems that are losing organic matter? So take the same situation, but assume a decrease of 0.01% of organic matter. This would mean that we're actually losing 30 pounds. So that 30 pounds of nitrogen has to go somewhere. If it doesn't end up in our crop, that nitrogen is available for leaching. So here we've got an even bigger potential problem. On the order of 60 pounds would be available for leaching in this scenario. So what does this mean in the context of WIXT? Well, thankfully, collaborators here at UW have done some really nice work to systematically sample soils from these plots over time, early on in the experiment, and then in Greg Sanford's dissertation in 2009, and then again by Dietz and colleagues in 2019. And so they recently published the soil carbon data. We're in the process of working up the nitrogen data. This is a first stab, just assuming that we have a carbon to nitrogen ratio of 10:1 in our soils. These are the kinds of changes in soil nitrogen that we would expect. And what you'll notice is most of these cropping systems are trending downwards in terms of their nitrogen, on average losing, from 1 to several thousand pounds of nitrogen across the whole soil profile over the 30 years of between these measurements. You'll notice on average, these rotationally grazed pastures have tended to accumulate a small amount of N. Again, I'm not talking about statistical significance, but these are the overall trends that have been observed in these systems. So what does this mean for nitrate leaching? So the key point, right, even though these red arrows are approximately balanced for most of these cropping systems, the fact that we're losing nitrogen that was stored in soil organic matter means that we can potentially have a nitrate leaching problem in these systems. And, back of the envelope, there's on the order of 30 to 70 pounds of nitrogen that's potentially available for loss from these systems simply because we're losing nitrogen that's been stored in soil organic matter. Okay, so how does this play out? So again, I'm going to show you these results from the partial nitrogen balance and then combine this with what we measured in the soil. So remember I mentioned before, in the case of these rotationally grazed pastures, we actually saw a slightly positive partial nitrogen balance, scratching our heads a little bit. So where is this nitrogen going? So we were really sort of surprised to see that this matches almost exactly what is actually measured in terms of the soil nitrogen change. And so we had this small surplus. It appears that this nitrogen produced from biological fixation may actually be stored in soil organic matter in these systems, with the caveat, right, there's lots of variability in both of those measurements. For these other cropping systems, unfortunately, the result is that even though we're close to neutral for our partial nitrogen balance, the fact that we're losing nitrogen from soil organic matter means that we have potentially tens of pounds of N per acre that's vulnerable for loss, either as nitrate leaching and or loss of gases emitted to the atmosphere. Okay, so what does this mean? I think there's good news and bad news. I think this is sort of a powerful application of this nitrogen balance approach to cropping systems over time. And I think the good news is suggests that if we're following approximate extension recommendations for nitrogen inputs, what we're able to harvest in our crops is penciling out, right? We're pretty close to neutral nitrogen balances for many of these cropping systems. The bad news, though, in sort of these traditional systems with lots of soil disturbance and long periods without living cover, if we're losing organic matter, this is going to be another source of leachable nitrate that we have to think really carefully about, right? And so I think that the take home is that really effective nutrient management is necessary, but not always sufficient to help us with nitrate leaching, particularly when we're dealing with, fine textured organic matter rich soils. Obviously, the story is going to be different in different parts of the state, especially if we're thinking about the central sands and the scenarios that go along as talking about in the first part of the webinar. But I think we need to really think carefully about these whole systems for sustaining and building organic matter in conjunction with our efforts on nitrogen management. So again, I'd like to acknowledge all of the folks that actually collected the data that we were able to synthesize for this experiment, and I'm happy to have some questions and discussion if there's time.
Great, thank you so much, Stephen. Great presentation. We've got a couple questions in the Q&A box, and welcome for people to continue to put more questions in there. And so I can dive right in. There's a couple questions for go along. First question about legumes ahead of potatoes. Is there any risks because of insects like aphids?
I don't know. That's a great question. I think we'll get back to you on that in terms of the agronomics, and I'm sure we'll have answers.
Sure.
Yeah, specifics.
Sure. Another question, you were talking about, different perennial grasses for forage. What about hayed, grazed pastures or other types of systems?
Yes, great question. I think from the nitrogen balance perspective, right? And as Stephen was talking about it um, in his presentation, it will for sure increase. I think there are several benefits to this, right? Increase soil organic matter over time. But within the central sands context, it becomes a little bit more complicated because now we have most of our soil has less than 1% of soil organic matter, right? So is the goal to build more soil organic matter, or is the goal to more carefully manage the nutrient from the fertility side? I think it's a combination of both potentially. And one other, I guess, barrier I've heard from growers when I talk to them about like, hey, can you have some animals grazing on your off potato years? Um, some of them have actually tried that approach, but suffer from the potato year because of the pasture. Because when you have 2 to 3 years of pasture, it builds this thick layer of root mass, right? And when you're trying to break it up again to plant potatoes, it becomes difficult for the equipment, and it does a decent amount of damage to the equipment itself. So I think I'm very hopeful that incorporating a perennial system into the potato crop rotation is it can do goods for the nitrogen balance side, but we will need to overcome those barriers first.
Great, thank you. There's a question here for Stephen. I think it's referring to the WICS trials. Do the dairy, the corn alfalfa rotations, uh, for the end balance estimate, do they harvest corn for silage or corn for grain?
Great question. They actually do both in the subplots, and so we can dive into the details. We've sliced the numbers both ways, and for this perspective, it sort of comes out in the wash. The greater variability is essentially associated with what we're assuming from the alfalfa for nitrogen fixation. But the key point, I think, we're still pretty close to neutral under those different scenarios. Yeah, great question.
Great, thanks. Another WICS question, can you distinguish whether excess N is lost or taken up by the crop when plant available N is deficient?
Yeah, so that's a great question. Coming back to what we're doing here, this is really a black box approach. And so we don't really, from the data that we have, we can't say what's happening to any given molecule of nitrogen. We can say what's coming into the system and what's leaving and what the change in storage is over 30 years. And so those sort of questions are not they're not addressable with this data, and they're not really relevant to this particular story. I think our question is, what is coming in and what's coming out, and are those in balance over the long term?
Great, thank you. There was one question, I thought it was a great question, go along, had typed the answer, but there's time to answer it live too, if you don't mind go along. So the question was, when you were talking about your shoulder season cover crops, when is the N sequestered subsequently available? So, thinking throughout the year about those cover crops.
Yeah, that's a great question. Hence, like if you go to the Q&A tab, it's a long answer.
Mhm.
So in the sands, it's a fast-paced mineralization scenario. So if you have cover crops up until say right before you plant the subsequent crop, whether it be sweet corn or potatoes, you have to think about when you terminate it and how much nitrogen is present before you terminate it, right? Because once you kill the cover crop, um, then there's no longer active nitrogen uptake, meaning that that organic nitrogen needs a place to go. So I guess the key is try to find and decrease the amount of time from termination to planting your major cash crop to make sure that there is active crop nitrogen uptake during the season so that organic nitrogen can mineralize into inorganic nitrogen to be available for your major crop, hence serving the purpose of nutrient retention for the shoulder season, right?
Great, thank you. And the second question, I guess, second part to that question was how do growers then know how much and to credit that crop?
Absolutely. I'm going to use an anecdote to answer this. Last year, I worked with a grower within the Central Sands who was interested in how much nitrogen their cover crops, including crimson clover as well as rye, did for their subsequent crop, which I think was a sweet corn. So basically, we took samples of the biomass, above ground biomass, and there was a extension article on how to do that that I answered within the Q&A box. So feel free to check that documentation off. And then also it's basically taking the biomass and then you can either use book values or um, the numbers from the documentation to make a rough estimate on how many pounds of nitrogen you can essentially decrease from your either manure input or synthetic fertilizer.
Great, thanks, Long. Yeah, I will share the QR code right now for your CCA credit, and happy to answer some more questions if people want to continue to put them in the Q&A box. I see our end of webinar question popped up. There's 2 questions here. Again, happy to hear feedback, and we use this evaluation data to further our work. So thank you so much, everyone who has joined us today. And again, we can stick around for another couple minutes if there are any more questions.
Laura, I think there was a question in the chat to us
Oh.
about biochar. And
Oh, great.
yeah, the question was, have you ran any trials with biochar in the Central Sands yet? Not that I know of, but we've had conversations about this within the Central Sands area. I know Stephen is working on some amendment work too. If Stephen, you want to touch a little bit on that too.
No, we'd love to do some of that work. The challenge is getting enough biochar to do an interesting project, and there's been lots of discussions about possible ways to make that happen. But I know there's a lot of interest, and I think in building more capacity to temporarily store nitrate, there's a lot of potential for a biochar. But I think that it's also useful to think about the nitrogen balance. At the end of the day, if we're adding more nitrogen than we're removing in our harvested crops, regardless if we have a place to store that, whether that's with biochar or in other bound in soil organic matter, we have to fundamentally figure out a way when we're going to get rid of that nitrogen from the system. Otherwise, we'll eventually lose it to our waterways.
Great, thank you. And thanks, Golan, for seeing that. Okay, well, again, we can stay on for another minute or 2, but I want to thank everyone for spending time with us this afternoon and asking some great questions. We invite you to visit our website for more content on this topic. And we did record this webinar, and we will post it up to YouTube within the week or so as well. We have our next webinar next Tuesday, March 11th. And yeah, have a great rest of your day. We appreciate it.